Egunon guztioi, egunon, kaixo. Buenos días a todos. Es para mí un placer dar la bienvenida a todos vosotros, en particular a Carlos Conca y su familia. Y yo aquí poco voy a hacer. Quería presentaros, I would like to introduce Mrs. Iratxe de Madariaga. She is the consul of Chile in Bilbao. I don't know whether you're from Chile, from Basque Country, from both probably, but she's a great representative both of Chile in Basque Country and of Basque Country in Chile. She has been from the very beginning involved in the organization of this event. We are very glad that of her support, and also especially that she accepted to deliver these say introductory few words.
Bueno, sigo en castellano, que bienvenidos. La verdad es que yo en este foro, que todos son matemáticos y tan expertos, no sé muy bien qué hago introduciendo, pero hay una gran presencia chilena y además aquí estamos homenajeando a Carlos Conca, que ha sido su cumpleaños y bueno, es un premio nacional chileno, es una gran persona, bueno, es una suerte tenerla aquí en Bilbao y también contar con tanta presencia chilena aquí, que creo que hay como en torno a 25 personas que han venido. También hay mucho francés por lo que he visto y gente un poco de todas partes del mundo. Bienvenido a le français aussi, qu'il y en a plein aussi pour ce que je vous. J'espère que vous seriez très bien ici entre nous à Bilbao. Je sais que beaucoup vous êtes venus assez souvent, donc bienvenue. In English as well if you want, because maybe others you don't understand. So as you can see, I can talk well, quite a few languages, but anyway, welcome to Bilbao. I hope you will enjoy your stay here. Well, I thank Enrique for inviting me to welcome you all and to introduce this science or these days that you are going to working days that you will have here. And I hope you enjoy it, and welcome especially to all the great Chilean representation, especially to Carlos Conca. We are celebrating his birthday here, and it's a great pleasure to have him here with his family. And I hope you enjoy it here. I don't know what else to say, and maybe I will pass the word to whoever, no? I
think it's Jaime.
Jaime. Well, con esto. Well, anyway, welcome to Bilbao. And, well, and anyway.
I'm going to present some photos, some pictures of the life of Carlos, some moments of his life. Maybe several of you will appear here with more hair, imagine with less. But principally, you know the history of Carlos. He spent several years in France, in Paris. This one was the reason that we decided to make the Congress here. And Carlos loved France and the French culture. For that reason, maybe you can recognize several of the cafes in the street when Carlos was talking with them. And later, Carlos arrived to Chile. Fortunately, some of you have been the opportunity to visit Santiago, to visit Temuco, a nice conference in year 2000, where some of you appear. This is a picture in Valparaíso, also in a congress in Valparaíso, where I spent nice time, and also appear Spain. This is a summer school in Almería. This is summer school in El Escorial, I think. Yes. Later in Santiago, Carlos returned to make his career with a lot of success, always share a good wine and a good food in Santiago. One of the things that Carlos loved a lot of is to make some barbecues in his house. Lola knows very good that. And this is part of the people of the department. As you know, Carlos stayed in the Department of Mathematical Engineering in Universidad de Chile, and also he is member of the CMM. And well, you know that Carlos received several prizes. Later, you will Reward and the rest will talk about that. But one of the two principal things that you love a lot of was the honoris causa doctor honoris causa in University of Metz, and the National Prize of Science in Santiago. Okay. Here we have some pictures. Here's Carlos with his family, with Maite. And this was in Valparaíso also, I think. No, in Colegio Fons. Yes. And this was in Chile for the conference of 2000. Yes. Carlos sharing his house with us, always with a good wine. He loved that. This is for the National Prize in 2003. Yes. And here is with Yanis and Jean Paulin in University of Metz when he received the Doctoris Honoris Causa. Okay. Well, here the dinners in the house are with Carlos. We share a lot of that with, and we enjoy a lot of. Here Pierre Otaret, which unfortunately he came here. This was in the school in 2000 in Temuco. Yes. And this is with people of the department some years ago. Okay. Here is one where was the visit of Professor Jacques Lyon to Chile. This was in 2001, I think. Or 1983? No, later. This is in 2000. In 2000, yes. And these are more recent pictures of Carlos in Nancy, in Valparaíso. This is in one of the nice views of Valparaíso. Okay. One of his friends, François Murat. Luc Tartat is also here. This was in Paris, I think, when you went for some habilitation or something like that. Okay. Well, François appears in a lot of them. Okay. This was my house.
Your house?
Yes, this was in my house. Yes, my own house. Here is with José Carrillo. He's president of Universidad Complutense now. This is Gustavo Perla and some people in Santiago. And with Lola sharing a holiday. Okay. Well, the idea is to have and share a moment with this. Happy birthday, Carlos, and enjoy this party.
Thank you very much.
Be brief, then you can take a nap. Huh? So we are here not only to watch pictures and see that Carlos is a very heavy drunker, but we are here to see that to celebrate Carlos' birthday, 60th birthday. He's our friend, he's our colleague, and he's also a very distinguished mathematician. So as you all know, Carlos is born on November 3rd, 1954. He graduated as a math civil engineering at the University of Chile in 1977, and then he went to France where he got 2 theses, because at that time, you know, we were a very rich country, so we could afford 2 theses. One, the first one, which is called Thèse de troisième cycle in 1982, and then his Thèse d'État, the serious one, in 1987 at Paris 6 University. Then he was, during that period of time in Paris, he was a researcher at the CNRS, and then he moved back to Chile, where he's now a professor at the University of Chile. So you probably already read in the small brochure that he received many awards, including the National Prize of Science in 2003. He's a member of the Chilean Academy of Science, and as you've seen on one of the pictures, he's also a Doctor Honoris Causa from the University of Metz. You know, he's the editor of many journals. He had many PhD students, many collaborators. He's a very well-established mathematician. I will not discuss today about his main contribution in the theoretical and numerical analysis of partial differential equation. Tomorrow, I will still indulge myself in saying a few words about his work. But now, behind the scientist, the mathematician, there is a friend, a colleague, a father, Lola, Maite, a husband, and that's a very nice human being that today we want to celebrate, right? Carlos had many friends throughout the world. So, you know, we've seen Vani, you are here, coming from India, some people coming from America, many people, many colleagues in Spain or in France. He has played a major role and is still playing a major role in the Chilean and French relation in mathematics, and that's, of course, something for which I am very keen. I am, and I guess we are all very happy to meet here with a common denominator of appreciating the friendly presence of Carlos, his generosity, kindness, and sense of humor. And we are not just here to talk about mathematics, also we are very happy certainly to hear very nice conferences, but we are here to enjoy some good time of friendship and to tell you, Carlos, feliz cumpleaños, happy birthday. And, you know, I did something wrong. Okay, you know, I just can't believe it that you turned 60, you know. I mean, you look the same as when we met first time 27 years ago. So anyway, thank you to all of you for coming here, and let's congratulate Carlos for his 60th birthday.
I'm impressed for this reception. I don't believe it very much. It's like it is like a dream come true. So I have prepared an official speech that I'm going to read in English. It is not my native language, but in mathematics we are used to do everything in English. So I would like to begin by thanking all of you for attending this reception and for the warm words of the speaker who came before me, in particular those of Jaime and Gregoire, who gave a very flattering portrait of my contribution to science and to some details of my personal life. They are both mathematicians of great prestige and for whom I have enormous admiration. So their words are particularly meaningful to me. My warmest thanks go also to Ms. de Madariaga Ibarra, the consul of my country here in the Basque Country, which finally it is also my country. So I would start by remember some moments I lived last year in China at a conference in Shanghai, China, organized by the University of Fudan, where one of our friends, who was in one of the pictures here, Luc Tartar, which is also an eminent French mathematician, he posed the question, why Albert Einstein was considered a genius. And not just among physicists and scientists in general, but by everyone in all parts of the world. Let us not forget that the Time magazine named him Person of the 20th Century, and that its final front cover in 1999 was dedicated to him. There cannot be doubt that Einstein's scientific achievements are some of the most important and far-reaching that the human mind has achieved. Yet, in Luc's Tartar's open-ended questions, I see something that leads us beyond rational abilities. It allows us to connect with one of the fundamental characteristics of our consciousness, to understand the prolific and prodigious interaction that exists between cognition and emotion, the root of all our behavior. Einstein was extremely accurate in understanding their fellow men. He was able to grasp the motivation of human beings, their hopes and their sufferings. He was very successful, but above all, he was of value to society. And very early, he came to live his life for others. In this way, he was exceptional in his community. And if he were to have been a mathematician, we would not have been so surprised, since all mathematicians are trained to serve, not to dominate. There are no mathematicians who are bad teachers. Moreover, we have the gift of teaching, and we invest time and effort in cultivating this talent. The creative expression of the mathematicians combine a certain duality. Like artists, we seek to recreate new worlds. Beauty is our guide. Yet, with the mind of an explorer, we also attempt to build a better understanding of the world that surrounds us. Experience shows us, however, that the work of the mathematician only takes on true meaning at the moment that it flows through the learning-teaching process and becomes useful in the mind of the student and disciples, in the mind, the célèbre, as my mentor Jean-Pierre Puel would say. Teaching is an art. There are no two classes nor two courses that are the same. The greatest happiness comes from giving classes to fresh men. Nothing makes us happier than scholarly adventure to the limits of the truth, with the sole aim of unraveling some unexplored detail of a concept, a calculation, or a theorem. This is the happiness that comes with each revelation. In the mythical 55-65 hallway of Paris 6 laboratory, my master François Murat used to exclaim aloud the famous French expression clarté lumineuse to capture this magical moment. I would dare to suggest that this is mathematics' greatest contribution to mankind, to have stimulated the development of psychological forces in the mind that ask for irrefutable and rigorous explanations. One of the distinguished mathematicians of our time, the Frenchman Jacques-Louis Lyons, shed light on this area with his work. He brought us close to the limits of mathematical modeling, leaving us the challenge of making the invisible visible. The greatest satisfaction of a life dedicated to mathematics is the people with whom one has shared ideas and stimulating debate. I cannot mention each one of you by name, nor were or able to present today, but now that I am very grateful to all those with whom I had had the privilege of collaborating and sharing my academic life, learning, teaching, and creating new mathematics. Reaching the age of 60 called up a number of feelings, including, of course, those that come from looking back over a life lived. The meaning of one's achievement in life can be summed up in one very simple observation, which is that they depend on luck. It was my luck to be born in Chile, a country that in the 19th century was affectionately nicknamed the vast Republic of Latin America, Euskal República Latinoamericaco. I don't claim to embody the hopes of those talented Basques with their generous and illuminating spirit who arrived in my far-off land centuries ago. Those whose dream of forming a free republic through knowledge and education could be symbolized by Don Andrés Antonio de Gorbea, the mathematician from Álava. These men and women truly took part in the events that shape the history of the Basque Country and Chile. It was a Chile where was all to be done, and even today, the motivation is high captivating. Gorbea led the Chilean Academy of Engineers. He cemented and modernized the teachings of mathematics, and in 1843, he founded the School of Physical Science and Mathematics at the University of Chile, which is the alma mater of Chilean engineering. Everything was placed in our hands for us to honor, extend, and transmit to generations that follows us. How could I stand before you, decorated with the honor that you have granted me, if I didn't feel proud to have taken some small part in this mission, which crystallized into the development of mathematics in my country? Thus far, I have mainly touched upon issues related to our professional practices, but I believe that this is not the core of life, being our human qualities and relationships the most important and determining factors. It is what you are about. It has now been over a century since my grandparents and ancestors left different towns in Europe, searching for a better future. They came to South America, arriving in Chile. I had the privilege of being able to return to Europe, and I felt as though my family has never left. This must surely make you proud of the strength of this ability to transmit and share such a cultural treasure. When I look back at the things I regret or that caused me joy, I realize that most of my experience are related to the people who surround me. I have been fortunate to have my parents, my wife and my daughter, who are both here somewhere in the audience, as well as my close relatives and friends, many of whom are dedicated to academia around the globe. Because at the end of the road, what really counts are the feelings you share with those who are close to you. Thank you to all of you. Thanks very much. Gracias. Bueno.
The Free Republic Conca 60. And we move to the scientific program. Our first chairman will be Jaime Ortega.
Well, I have the pleasure to introduce Professor Juan Asenjo. He's a titular professor at the University of Chile in the Faculty of Science, and also he's the president of the National Academy of Science. It was a real pleasure to introduce Juan, and an honor to be here. He will present a talk, Mathematical Modeling of Metabolic Network with Gene Regulation. Okay. Okay, thanks.
Okay, good morning. It's a real pleasure for me to be here, particularly since I'm not a mathematician, but I'm here as president of the Chilean Academy of Science, and I have collaborated with Carlos for many years. I know some of you, like Angela Steffens here, or some others that I've known for a few years, because I'm an engineer by training, and I've always been collaborating with mathematicians. I move a little bit in the biological world, but without having ever had a course on biology. So I learned on the job, and that's why I'm going to tell you about metabolism and genes. Two different things, right? That's about all you need to know. IANAS is the Inter-American Network of Academies of Science. It has all the academies of science in the Americas, including Royal Society of Canada, National Academy in the United States. And at present, I am co-chair together with Mike Clegg, who's Foreign Secretary of the National Academy in the United States. Chile has a very visible internationally, it's very visible in science in general, as you probably know, and otherwise we wouldn't be here. Okay, the 4 countries that have more presence internationally in science, I guess it's Argentina, Brazil, Mexico, and Chile. And in terms of productivity, I think Chile is still the highest. And also Chile in 2010 became a member of the executive board of the Global Academies Worldwide, which is 107 academies of science in the world. Okay? This is a meeting in Santiago. If you've ever been to the Academy of Science, this is where we meet. the academicians. Carlos, we were there 2 weeks ago, right? This is the library of the Academy, which, if you happen to go to Chile and visit the Academy, is a very nice room. There is Lorna Castleton from the Royal Society. Pierre Lenat was there from the French Academy, who's had a lot to do with Chile and also in science education. Pierre Lenat is very important. Chile and the Académie des Sciences de France and the Royal Society have very strong ties in everything that has to do with teaching science. One of the weaknesses in the world has to do with teaching science, not only in developing countries or half-developed countries like Chile, but also in different parts of the world, okay? And our academy is very active in that. Now, today I'm going to talk about very simple biological systems that developed 3,000 million years ago, which are bacteria, or 3 billions of years ago. If life started here 3,500 million years ago, or billion years, whichever you want to call it, I'm going to talk to you about bacteria and yeast. Yeast in French is levure, or levadura in Spanish, and has a lot to do with us, right? With people who like wine, okay? Yeast has two important roles. Yeast by itself, no, nothing interesting, but yeast with grapes is older than our species. That's why there are films of elephants and gorillas eating fermented food in Africa and getting drunk and being happy. It's also used to make bread, okay? Now, we just heard about Einstein being the most important human being, scientist in the 20th century. Now, there is another gentleman who was quite important, but the century before. Okay? He was a young Englishman, and he traveled for 5 years around the world. But what you may not know is that he spent 2 years in Chile, going from the south to the north, back to Argentina, and so on. And when he traveled in a ship called the Beagle, which was no longer this room, okay, he was seasick almost all the first part of the journey. He wasn't used to traveling in a ship like this, you know, in the Atlantic, which we now cross in a few hours, several of you who are here. But he came in this ship with a very young Admiral Fitzroy. And Fitzroy had been to Chile 2 years before, making maps for the great British Navy, right? But when he was here 2 years before, he took some Fuegian Indians back to England. And the Fuegian Indians learned English, they dressed like Englishmen, and one of them, the best known, called Jemmy Button, he was in the ship with Darwin in the Beagle, and he told Darwin how he could speak with animals, because he lived amongst animals in Tierra del Fuego. And when Jemmy Button returned to Tierra del Fuego, he took off his clothes, his English clothes that he loved, he went back with the Fuegians, and Darwin couldn't believe it, because he called these Fuegians degraded savages, Darwin. And when this gentleman went back and became a degraded savage again, Darwin said, well, there isn't that much difference between animals and human beings. And that's how he started thinking and developed his theory. Afterwards, he saw an earthquake in Concepcion where the earth moved. He saw the Volcano Sorno exploding. And also, when he crossed to Mendoza, he saw marine animals in the rocks, okay? And those three elements were critical for Darwin's theory, which revolutionized thinking, scientific thinking in those days. Also, it took him, however, he started writing his theory 37, 38, it took him 20 years to publish it, because his wife was very religious and went against the establishment. And there are lots of stories, but Chile was very important for Darwin, okay? Not for Einstein, I'm sorry. So, the only thing you need to know about biological facts is that there are these simple animals called bacteria. Bacteria have a chromosome, the DNA, okay, genes, but when human beings started killing bacteria with antibiotics, antibiotics were discovered in 1928 by a gentleman called Fleming, but he never realized that they could be important, okay? And it was until the Second World War started, okay, that Florey in Oxford, an Australian scientist, he thought they could be useful, and then 3 people got the Nobel Prize in 1945. The same year, a Chilean poet got the Nobel Prize. It was Chain, who was a German biochemist who purified it, Fleming and Florey. Fleming was made Sir, but Florey was made Lord. Somebody knew the difference between realizing what is important and only discovering it, okay? So when human beings started killing bacteria with antibiotics, bacteria didn't know how to defend themselves. So they invented the resistance to antibiotics. And human beings didn't know what was happening, like today, that there is a lot of resistance to antibiotics, and the resistance to antibiotics is in extra chromosomal DNA called plasmid. So this is very important because plasmids can come out and come back in. And in the 70s, people could put a human gene into a plasmid and produce something useful in bacteria, okay? And this human gene was the gene of insulin. Okay. You know what insulin is? You know that some people are diabetic. Wealthier people, fatter people, better diet, China, you name it. Okay, diabetics are increasing in the world at an incredible rate. So now these are called, since this is recombinant DNA, these are called recombinant bacteria, bacteria that can make a human protein. The same happens to yeast, and this is all you need to know about biology for our model. Now, this is Chile. Has the most incredible variety of weather, of conditions, okay, and from the driest desert in the world, from where we're getting bacteria now that make new antibiotics, to the coldest part of the world. If Chile was like that, it would be no fun, you know? But as it is like this makes it very important for the genes that you can find in the country. Now, we have a new building. I don't know if Carlos Conca has told you. The School of Engineering has just built almost like a palace, okay, like a Hyatt hotel has been just inaugurated. Not even a university in the developed world have buildings like that, and it's quite tall. So this is the view from our new building. It has to be a very clear day, and you need very good eyesight, okay? Anyway, originally, biologists used to take apart the eye, study each reaction, and then they thought they could understand the whole. But it never works like that, you know? So what we need to understand is networks. When the human genome was sequenced, everybody thought it was going to be 100,000 genes because it's 1 million proteins. No, it was only 30,000 genes, the same number of genes as a worm. Now, knowing some human beings is not surprising, but the point is that the complexity is far beyond. The complexity is the network, okay? The psychology of worms is quite simple compared to the psychology of human beings. So, systems biology, as we study in our new center, studies networks. This is something typical, you know. Students say, oh, we are not in Harvard, we're not in Cambridge, we cannot compete. And I tell them, look, a scientific paper is the product of the mind, not of a robot or a machine or a computer. It's an intellectual exercise. So this is our new center, which started in June, on which Carlos is one of the key scientists. The center has 5 areas. Metabolic engineering, what I'm going to talk to you about it a bit today, and mathematical model and the relationship. And Carlos is the key scientist in the mathematical modeling part. Also, bioinformatics is very important, and so on and so forth. So this is what I'm trying to convey to you in my talk. Ramon Gonzalez was a PhD student of mine who is now associate professor at Rice University in the United States. There are many bright Chilean scientists who go and do PhDs in Germany, in France, in the UK, in America, and then they're hired as academics like Carlos was, or like I was in the United States and then in England. But very few with a PhD from Chile become hired in universities of the developed world. This is something, this is metabolism. This is what's happening in all your cells at the moment. This happens in bacteria, this happens in yeast. It's common to almost all live cells. When glucose goes into the cell, okay, makes proteins and so on, energy, somewhere here is the ethanol, right, because this is yeast, very important, CO2. So basically, this has 80 reactions, a very simplified metabolism. This is called glycolysis, this is called TCA cycle. This all occurs inside of a cell. Now, the secret is that if this is a cell, when the cell is doubling for, or so to say, growing exponentially, 2, 4, 8, 16, 32, 64, all these rates are fixed because the reproduction rate or the growth rate is a constant. So if you measure the glucose that goes in, the ethanol that goes out, or the CO2 that goes out, you can calculate everything that's happening inside the cell. This is something the biologists would not believe us until we demonstrated to them that it was true. So this is, metabolic flux analysis is a very important tool for a number of reasons. Here you can't see very well the lines because the projector is behind, right? But this is time, okay? This is glucose, cells, and ethanol. In a so-called fermentation, the glucose is consumed, okay, and then ethanol is produced, okay? This is normally what you use yeast for. Now, if there is no more glucose available, then the yeast cells use the ethanol. But normally, in a fermentation, to make wine, to make something else, okay, is the ethanol that is produced is important. But what is important here is that first glucose is consumed. This is the easiest sort of carbon source to be consumed. And when the glucose runs out, then the ethanol is consumed. Of course, if you look, yeast grows faster on glucose than on ethanol because it's what yeast normally does. Okay? These are other materials that were measured, carbohydrate, protein, RNA. And as I was telling you, strain P+, it should say there, is a recombinant strain. This is a yeast that makes a human protein superoxido dismutase, that is responsible for oxidation in the human body. Now this one doesn't. This is P-, this is wild type, non-recombinant. So glucose is consumed almost at the same rate, but here, since there is this burden of making this protein, which is a human protein, the cells grow slower and the yield is not as high, okay? But in both cases, first glucose is consumed and then ethanol is consumed. And in glucose, the cells grow faster, in ethanol, they grow slower, okay? So these are 4 facts, recombinant, non-recombinant, and the other fact is, okay, so the maximum specific growth rate called mu, is faster, of course, in glucose than in ethanol, almost double. And for the other strain, our aim was to compare these 2 strains, but what happened to be more interesting in the end in the paper, you never know when you start doing research what's going to come out, okay, was the comparison between the cells going on glucose and growing on ethanol. This is the only thing you have to keep in mind. And with our system, we could measure all the rates inside of the cell with our system of 80 equations roughly, and we said, we predicted glycerol was going to accumulate. We had not measured it, and when we measured it and it was accumulated, then the biologist said, this can be used for something useful. Okay, this is the other part. So, and genes expression. As you know, there are techniques today called microarrays where you can measure the expression of genes in any cell of the human body. People say this is going to revolutionize medicine because by measuring certain genes you can tell if the person is going to develop a type of cancer, etc. So we had very sophisticated equipment of a colleague of us in Manchester in the UK, and we sent a student and he measured all the expression of the genes. So he was comparing the way the cell was behaving, metabolic flux analysis, what the numbers I've just shown you, with gene expression. Okay? Are we really what our genes say? This is just the typical slide of the almost 7,000 genes of yeast. And then if the genes are overexpressed, the numbers are red. If the genes are underexpressed, the numbers are green. And here we were comparing what happens when the cells move from glucose to ethanol. We saw that the cells grow slower on ethanol than on glucose. So if in the change from glucose to ethanol, genes are underexpressed, these numbers should be green. And the numbers are red because the genes are overexpressed. So in this particular case, which is the only case, it is not possible to correlate in a direct function gene expression with cell function. Okay? The genes are overexpressed and the cell is slower. This is not the case when we pass from ethanol to stationary. Here the cells stop growing, so you expect the numbers to be green, and they are all green and very large. Nor when we compare the recombinant strain, which was slower than the wild type, which was faster, numbers are green, quite small numbers. Okay? So we prepared the publication, Global Gene Expression, where we compared the metabolic rates with gene expression. We wrote the paper, we sent it to Steve Oliver in Manchester, we never had an answer. So Andy Hayes was also from his team, and Juan Castillo also from his team. So we sent it for publication. As soon as it appeared electronically, they started writing back and they said, oh, my address has changed. They didn't change a word on the paper. I think maybe they weren't convinced that this finding of our PhD student Humberto Diaz, that when the cells grow slower, that the genes are overexpressed. I'm not sure if they didn't think it was right, but afterwards they had a whole day symposium in this lab. Oliver is now in Cambridge on this paper. It's the only case where there is not direct correlation between gene expression and the behavior of the cells. Also, Humberto Diaz, when he left for 6 months to England, and his little son was born just before he left, so he worked day and night. So in 3 months, he completed the work. So Oliver wanted me to send him more Chilean students. But anyway, let's continue. So now we're going to try, we have talked about metabolic networks. So the next challenge was how to relate now metabolic networks with gene regulation. And first we looked into yeast. Before we had 80 reactions. Now we have only 39. We simplified the system, okay? But we have genes and enzymes. Behind each of these reactions, there is an enzyme, a protein that makes the reaction go faster or go slower. That's with the well-known Michaelis-Menten kinetics, right? By the way, the Michaelis-Menten kinetic was first discovered by a Frenchman called Henri, but the publication was in French in 1898, so everybody knows it as Michaelis-Menten equation. Fair enough, happens with a lot of things in science. So now here we have regulation. You see, glucose, when glucose is present, it induces the genes that synthesize the enzymes that are behind this reaction. So here we have a chemical product that is regulating that these enzymes are produced at the gene level. And here is repression, okay? These others are repressed. So when there is enough glucose, this goes like this, and ethanol accumulates. When glucose runs out, then ethanol is consumed. Okay, so this happens at the level of the gene that's synthesizing these proteins. This is the type of equation, simple differential equations, not even partial differential equations, which are Carlos' specialty, right? And this is typical Michaelis-Menten kinetics. So in total, we had this behavior. Now, before we looked at steady state in glucose first, then steady state in ethanol. Now we calculated this again. Obviously, the values here are the same, but as the whole system is simplified, some values changed. So we have two steady states. That's the only experimental values we have, and we have in total 72 equations and 120 unknown. So luckily, we have a good computer scientist who's a postdoc, Paulo Moisset, and he wrote like an optimization function, okay, and with some weights, okay. The weight coefficients is, for things that are preserved, a very high weight. Things that are measured, higher even. Intracellular concentrations that nobody measures, very low weight, and kinetic constants, intracellular kinetic constants, even lower. And with this optimization function, this has been published. We obtain good qualitative behavior when cells are growing on glucose, similar when cells are growing on ethanol. This is enzymes that are induced by the presence of glucose and enzymes that are repressed by the presence of glucose. So now we can run a continuous simulation of the whole process without changing any parameters. In other words, here is glucose induction and also repression. This is the growth of cells, and this is the ethanol. So we were very happy with these results, and then the reviewer of the paper said, what does your model say about the concentrations that you did not measure, intracellular concentrations? So that's how they say in English, the proof of the pudding. Right? And this is the results of Moisset, our paper, and very similar to data that had been published. None of these concentrations had been measured. And now I have another student who did this with Escherichia coli, a bacteria, slightly different system, because now we have again, induction and repression. There is glucose, there is galactose, and there is a third carbon source, glucose, lactose, and galactose. And we did exactly the same, and this is the simulation. This is the glucose. Sorry, the glucose is used first, then the lactose, and this is galactose that has accumulated. Okay, the only slight overshoot is there with the acetate. So this publication is now being prepared. So this, as Carlos calls it, reverse engineering methodology, okay? Again, we could use a much larger number of unknowns of equations, and the concentrations fit the same. This we are applying now to bacteria from the Atacama Desert to find new antibiotics. This is the team. This is from Scotland, Marcel Jaspers, Mike Goodfellow, and Alan Bull at 5,000 meters in Chile that you may know. This is, we were all a bit younger here, my collaborators, and the same group enjoying the product of the biotechnology and yeast industry in Chile. Thank you very much.
And do you have an estimate of how many scales are involved in the kind of phenomena you explained to us? Because it is clear a multi-scaled phenomena. So the mathematical model is much more complex. And the second question is which is the difference, for example, between ethanol and glucose? Because at a macroscopic scale, we are not able to distinguish between both. They are just molecules somewhere at a very small scale. So how can we distinguish these two different molecules? Yes.
Well, the first question, we can go back to Einstein, because he said that when you model a system, you have to model it in as simple a way as possible, but not simpler. It depends what your aim is to achieve at the end. Okay, you can have a very complex model, but which is far too complex for what your objective is. So you need to know the physical system you're modeling in order to make the correct model. If you only know mathematics, like some of your colleagues do, sometimes, and you don't have a feeling for the physics, it's very difficult to model it. Okay, there are some people in your center trying to model biological systems, but at the beginning they didn't know the difference between a protein and a gene. Okay, and some basics you need to know. Okay, the other is drink a glass of glucose, drink a glass of ethanol. I'm sure you can distinguish it, but these bacteria, and then go driving. I'm sure it will have an effect, But these bacteria have developed these so-called almost intelligent systems just over evolution, So whatever is more fit survives, or whatever is more fit lives longer than the less fit. So all these systems, why they grow faster on glucose, it's just because they have evolved in that way.
Yes, they are adapted to different situations or to different ambience.
Yeah.
This is what happens.
But evolution is more than adaptation. Okay, and that's the value of Darwin's theory. There used to be a previous theory to Darwin from a Frenchman, and he said you adapt, and those adaptations stay with you. They are genetic. But Darwin took from an economist called Malthus the fact that it's the better adapted that survive and not the less adapted, which is a slightly different concept, and it was also coined by another fellow, and both theories arrived together at the Royal Society, but it's known as Darwin's theory. Anyway, I don't want to take more time here. We were told to be very strict with the time.
It must be.
Anyway, thank you very much.
Okay, thanks again to Juan.
Of course, I have to thank the organizers, not only for inviting me, but mainly for organizing this very nice conference here. And so I don't know if it's, like Enrique said yesterday, something special for Carlos doing the conference here in Bilbao, but it's sure that it's something special for us. So we're extremely pleased and honored to be here, and in particular, for me, it's a great, great pleasure. So I met Carlos in Paris, of course, in Paris 6. And it has been, 86, yeah. And so it has been an example when he was in France, in Paris, because he was very successful when he arrived there. He was sharing an office with Maria Esteban, so I used to go there and see them. It was an example for us, of course. And then it was extremely successful too in Chile. And The good example is this amount of young Chilean researchers which are all around the world, and in particular some of them are here. So it's really impressive. So congratulations and feliz cumpleaños, Carlos.
Thank you.
So I would like to talk about a recent result we did with Bean, which is somewhere here. His name will appear in the precise result. But before, I would like to present a little bit the motivation, because the equation seems or may seem to be unnecessarily complicated. So let me try to motivate. So the idea is what we would like to do. So that's the plan of the talk. Try to generate the motivation, then present the problem, and finally the result. So what we'd like to do is to describe as precisely as possible a gas of boson particles at low temperature. So so bosons, what are bosons? As far as I know, so bosons are quantum particles, but different from what the better known, probably the fermions. The bosons like to be together. So the statistics, as I say here, do not restrict the number of them which are at the same level of energy. So you can't have two fermions at the same level, but bosons like to be at the same level. And that makes a lot of changes in the statistics. Now, what do I refer by low temperature? Low temperature, I don't want to give a precise definition of it, but for what I want to say, let me just say in that way. If you have a set of bosons, n bosons, which have a total momentum, say P, and an energy E, there is only one distribution giving the equilibrium of that set of bosons, which is given, the distribution function is given by that function n naught of t, which has a regular part. So I can move, which has a regular part here. Oh, I think I have. So you have a regular part here, an exponential 1 over an exponential function, and then a drag measure, a delta function here with a real coefficient. So given the number of particles, the momentum, and the energy, you can find a unique beta, mu, alpha, and p naught, such that the distribution function of the particles at equilibrium is given by that. Omega p is the energy of the particles. The key point is that the product of alpha and mu has to be 0. So either alpha or mu is 0. When alpha is 0, I will say, or we say, that we are at high temperature, or what I say here, supercritical or critical temperature. When alpha is positive, so mu is 0, alpha is positive, you have a Dirac measure in the distribution function, then we say that we're at low temperatures. When alpha is positive, we have a Dirac mass here, so we have, as I say here, a non-zero density of particles at some level at some momentum, which is p naught. Now, the particles that are in the condensate, so some of the particles are described here in these equilibria, are given by these delta functions. The particles in the condensate are described by a Gross-Pitayevsky equation. So one single wave function describes all the particles in the equilibria. That's one of the characteristic features of the condensate. And at 0 temperature, when all the particles are in the same in the condensate, all the particles are in the condensate. So this has been proved that you can describe this condensate by a function psi satisfying the Gross-Pitayevsky. In the non-stationary case, it has been done by Erdos and collaborators, and in the stationary case, it has been done by Lieb. Now, the particles which are not in the condensate, where you are not at 0 temperature, but at positive temperatures, you still have some particles in the gas. The particles in the gas are described by a Boltzmann type equation derived by Nordheim in 29. So there is no rigorous deduction of the equation. It's accepted in the physical literature, and we accept it. And there are some partial results, some partial rigorous results by several groups. Italian people Benedetto, people in, so Lukarinen is in Finland, I think, with Spohn, Fau and collaborators in France, which have partial results on the rigorous reduction of the equation, but that's still an open problem. Now, on this Boltzmann equation, you already, or we already have obtained several results, several interesting results about the global posedness of the problem, the Cauchy problem, existence of some particular type of solutions. Here I gave one of them, which violate the conservation of particles, which is one of the conservation laws of the equation. Existence of blow-up or of condensation in finite time for some solutions of the normal equation. But there are still a lot of problems, of course. So today I would like to describe the following. So consider you are at not only at low temperature, but at very low temperature. So you have your system with particles in the gas and particles in the condensate. So you will have a system of two equations. I will not write the equations, it's not necessary. So in that range, the interest of that range, the thing that motivates is that you may perform some approximations. The first one is that the main interaction driving the system are the interactions between the particles in the condensate and the particles in the gas. So you can neglect, at least it is considered that you can neglect, the collisions between particles in the gas between themselves. So you drop in your system of equations, you can drop one big part of the system, and you reduce only to study the collisions between the particles that are in the gas and the particles that are in the condensate. The second approximation you can do at very low temperature is that the energy of your particles, if you have a particle of momentum p, the energy is more or less given by the norm of p for p small. So we will take omega of p equal to modulus of p. That's it, for all p. So that's a strong approximation too. The third approximation we will do is that we will consider that the gas and then the condensate too is independent of the space variable. So the density of particles of momentum p, whatever the value of p, is independent of the position in the space. The gas is homogeneous, spatially homogeneous, doesn't depend on x. So that's a huge simplification. So I just wrote it here for the density of particles in the gas. N is going to be the density of particles in the gas. But it's also true, it's also assumed for the density of the condensate. Now the condensate in principle is described by a complicated and difficult equation. It is a Schrödinger nonlinear equation. If we consider that spatially homogeneous case, we can reduce the equation to an ODE for something that only depends on time. So that's a huge simplification. So the system now will be a Boltzmann equation which will describe the particles in the gas, and an ODE which will describe the condensate's density. The condensate, all the particles in the condensate have momentum equal to 0, so there's no dependence on p. P is 0, and there's no dependence on space because in the case of spatially homogeneous. Okay. And the question I would like to address is, what can we say about the relaxation rates of the solutions of the system to their equilibrium? There are equilibria, they are well known. We suppose that the solutions will converge to equilibrium. Can we say something about the rate? So why that question and no other? So the point is that it's well known that in this approximation, when you are at very low temperature, the collision frequency of the particles, so the mean number of collisions between your particles, is not bounded from below. So the number of collisions can be as small as possible. So and if you don't have collisions, you don't see what's the mechanism driving you to the equilibria. So, and you want to know what is the rate of convergence. So one understands easily that it's going to be something to do. Okay? So that's exactly the same situation as for the, when you consider the Boltzmann equation for classical particles, and you are in the case called the soft potential. So it's exactly the same problem. Yeah, more or less the same problem. And that was a question considered, well, some years ago now by several. So here are some of what I believe are the main, started with Grad, and then these two results were really very, very important. And then you still have some references. This is the most recent I've seen, but you have still a lot of work on that. So the point here, which is funny and allows us to obtain something which is, I think, interesting, is that the fact that the energy of the particle is like modulus of P has a very, very strong consequence. If we have particle P, P prime, and say, I don't know why I called Q prime, it should be Q, just Q. Denote particles with momentum P, P prime, and P minus P prime. And you look at the collision of the particle with momentum P prime with the particles of momentum P minus P prime. To give a particle of momentum P, the momentum has to be conserved in the collision. The energy too has to be conserved. So you need that P, P prime, and P minus P prime satisfy these two equations. And then the three vectors have to be collinear. That's no way. And that's a huge simplification in the collision integral of the equation. I don't want to write the collision integral. It's a mess, and I don't need it. But that allows you to simplify a lot. In particular, the delta of the energy, which is one of the difficult parts when you try to simplify your equation, that simplifies a lot the calculation of this delta of energies. And it reduces the problem to a radial problem. So what I'm going to describe is a non-radial result. I'm going to take a radial equilibria, but that's not a loss of generality. I will perturb with a non-radial perturbation, and the question is reduced to a radial problem, essentially due to that effect. So that's what so I think that I don't want. Okay. So I linearize the problem. Whatever is the equation, I linearize it. So I take a radial initial data. So that means I took P naught equal to 0 here, so that's radial, and there's no loss of generality. I can always make a shift in the momentum space to place the initial data here so that the energy of the particles is P, and I write my perturbation like that. So N naught is this, and omega is my new unknown. Okay? I plug that in the equation, and I just keep the linear terms, and I obtain the classical linearized Boltzmann equation with that I call L just for notation purposes. So W and M are completely explicit. W is a measure, you have some deltas here, and M is a function, it's an integral of W in some sense. So that's the equation I'd like to study with an initial data. I have to linearize to the equation for the condensate, but that's much simpler because, as I said, the equation for the condensate's density is just an ODE. So I just linearize around 1, and I get that equation for M, which means that as soon as I know how is omega, I know that integral, I know what perturbation. So that equation is true. Of course, the linearization preserves the energy of the total energy of the particles, but it does not preserve the total number of particles because some particles are in the condensate. And n is just, that omega is just describing the linear perturbation of my gas. Okay. Now, what is the surprising effect of this fact that the collisions are necessarily collinear? Well, I look for a solution of that linearized equation. I develop this, so I look at like a function decomposed in spherical harmonics. Okay? So these are the spherical harmonics, and these are the different modes of my solution. And I plug that in that linearized equation, and due to the fact that the collisions are collinear, I need to know some property of the kernel W. W, which appeared in the equation, in the linearized equation here. That W has also a particular form coming from the same fact that the collisions are collinear. But then we see that all the modes of the function omega, if I want a function omega satisfying the linearized equation, it is enough that all the modes omega Lm satisfy the same equation. These modes are now a function of t and r, just this is a real number now, I mean radial variables, and all of them satisfy the same equation. So if I'm able to solve this equation in radial variables, I'm able to obtain the function omega. Okay? So of course the initial data will be different. So all the modes satisfy the same equation, but with a different initial data, which is the data, the coefficient corresponding to the initial data, the Lmth coefficient of omega naught. So the problem, the non-radial perturbation is reduced completely to a radial equation. And now, well, you do the good change of variables, which was already known, so that's not something new. And you write the system or the equation that we really considered, which is very, very simpler than the original one. Okay, so almost everything is explicit. So the equation is this, where gamma is an explicit function. Gamma of k is given by that integral, where phi is k squared. So k squared over n naught times 1 plus m naught is 1 over sinus hyperbolic square. So the sinus hyperbolic is there because, let me just go back once. This product here is 1 over the square of the hyperbolic sinus. So the hyperbolic sinus comes very naturally. So that function gamma is completely explicit. Phi is that function is in the kernel, generates the kernel of the operator A, and the operator A is still, of course, a non-local operator, where you have an integral here with the kernel K, which is almost explicit. You have very good estimates of the kernel. And of course, what you can see here is that this function, when k goes to 0, where is gamma of k? When k goes to 0, that function goes to 0. So you don't have a positive lower bound for gamma of k, and that's the origin of our problem. Okay? We will not have what we call a spectral gap for this operator, and then the rate of decay will be. So just to say that. A good part of that work was already known. So the equation that I've just written was almost the same equation, was written, I think the first time I saw it by this guy, Vanier, in 69. Then it was the spectrum of the simplified equation when we took a coefficient to be constant, was studied by Claro and Vanier in 71. In that article by Bouot, you can see a quite precise description of the spectrum and compactness properties of the collision operator. And then in this reference by Benin, say he elaborates a little bit more about what was already known. So there were already several, perhaps in slightly different contexts. So that is done for gas of bosons. These people were working on the equation for phonons, but it was essentially the same motivation. So what's the result? So as I said, it's something we did with Chuan Min Bin, who is a young postdoc in Beacon. So the first result is just to be sure that we have solutions and we know what we're talking about. So and it's a result for this radial problem, which is in R+. So you take any initial data in L2, you consider the projection of this initial data on the kernel of the operator, which is that we project F0 on this function, which is nothing but the kernel of I normalized in L2 norm, and that's the projection of the initial data. So you can prove that there is a unique solution, which is, so the solution is bounded from 0, is global, takes values in L2, it's continuous with values in L2. If you take away the projection, you obtain something which is integrable in time with values in L2 with the weight gamma. The function gamma is the one appearing in the equation. So it's L2 of gamma is not, you cannot compare L2 of gamma and L2 of R+. It's not neither of them is containing the other due to the behavior of gamma. And the equation is satisfied in some weak sense, and the initial data is taken in the L2 sense, and you have some other behavior here. You have the conservation of the energy that you expect, so the solution satisfies the conservation of the energy. And if the initial data is non-negative, if you have a density initially, then you have a density, so it's f of t. Now, the rate. So if you impose on the function f0 to be slightly better than squared integrable at the origin, then you get a rate of convergence. So f of t will converge to its projection on the kernel of E, so that's what you expect. And the rate that we obtain is like 1 over square root of t. So that's what we. So it's an algebraic rate of convergence. It's not an exponential. I don't have time to compare it with what is obtained in the classical case. We don't know if it's optimal, of course. So just 1 or 2 remarks. So if we had E is my integral operator, that's the right of the equation. See, if we had an inequality like that, kind of a coercivity estimate, then the rate of decay would be trivial. Okay, we multiply the equation by f, we obtain that, and due to that, we obtain this, and that gives you the exponential decay, and that's it. Unfortunately, something like that cannot be true because gamma of k goes to 0. So that's excluded. You cannot expect something like that. That's exactly what happens for soft potentials. So now, what you can prove, the first step using classical spectral theory is you can't prove. So let me focus on that one. If we suppose that, you can always suppose that the projection of f0 is 0. You just consider the other part of your solution. Okay, so suppose that f0 is in the orthogonal of that function phi. Then this lemma tells you that. So here you have L2. Here you have a constant, which is with a minus. That's good. But here you don't have L2. You have L2 of gamma. And that is not enough to get to do the argument I just did before. It doesn't work. That doesn't give you any. There's no way. You can try. There's no way. So because here you have L2, here you have L2 of gamma, and you cannot compare in general L2 of gamma and L2. That is not less than a constant times L2. But that's useful nevertheless. And that's using spectral theory. Now, the second lemma, which is what we did really, says that if you have a solution which already satisfies that for some gamma, suppose you have a solution of your problem which satisfies this inequality for some gamma. For example, in the theorem I just gave you, gamma omega is 0, and that's true. For our solutions, we already know that for omega equal to 0. So if that omega should be greater than or equal to 0, of course, because we start the argument with omega equal to 0. So if you had something like that, then you can obtain something like that for some constants theta 1, theta 2, blah. So what do we say here? We are comparing the L2 of gamma norm, which is the bad guy at the right-hand side of our inequality, with the L2 norm, which is what we want, but we have to lose something. We lose that. But that's not too much. So now we use this inequality here, and we can close the argument and prove that we decay at least with a rate like 1/2. Okay, so that's the result, and I think I'll stop here. Thank you very much.
Okay, so thank you for the introduction, and thank you also for the invitation. I am very happy to be here with Carlos to share this moment. When I see the picture, I see some difference with now. But actually, as Grégoire said this morning, we don't see much difference when we look at you and we realize that we are here to celebrate your 60th birthday. When I look at you, when I don't look at me, but when I look at, as I feel, we don't realize that we are so close to the 60th birthday. Okay, so happy birthday. Alors, comment on fait ça? C'est ça, comme ça? Non, c'est pas ça. C'est... Okay, so I will speak about quantum chemistry. I've chosen the subject because interdisciplinary is an important field for Carlos. His involvement in applied math and at the university in France and in Chile in direction of interdisciplinary and in particular industrial application is an example. So another example is about multiscale analysis. Where he has been a leading scientist. So I will speak about a multiscale approach in quantum chemistry. So this is an important subject that has been attested, for instance, with the Nobel Prize in Chemistry by Karplus, Leavitt, and Warshel. And because trying to do the numerical simulation of molecular system is impossible when you start from the Schrödinger equation, because there are too many problems, unknowns to be taken into account. So this leads to the definition of different category, different multiscale, where, for instance, in the QMMM method, the combination of quantum mechanics and molecular mechanics, you try to do these different boxes at a different level to consider the molecule. And in this embedding process, you have to take into account the object you are interested in, for instance, a big molecule, a protein, and with the surroundings, the environment. And you have to take this into account because the environment modifies the structure of the molecule, and the molecule itself modifies also the environment. So there are different levels of taking into account this environment at the mechanical embedding level, where you do a pure classical connection with the surrounding, and this is only valid for ground state energy calculation. You take a little bit more into account by taking the electrostatic behavior, and this allows you to see the effect of the environment on the molecule. And if you want to go further again, to take into account not only the effect of the environment on the molecule, but also the fact that the molecule is polarizing the environment, you go to the polarizable embedding. And you have to know that 90% of the chemistry, roughly speaking, is taking into account into solvation. And where there is this reciprocal influence of the solvent on the molecule, so this is typically a multiscale approach. If you look at protein, so even if it is the charges are all equal, the positive and the negative charge are all equal, when you look at a large protein into a solvent, then part of the molecule will be charged positively and the other will be charged negatively. So the total is neutral, but nevertheless there are long-range actions due to the fact that the big molecule is charged in some sense, and if you want to take into account the solvent around the molecule you are interested in, a recent paper in 2014 has raised the point that for some cases you have to go up to a distance of 20 angstrom, which is very, very large. So if you want to take into account all the water molecule or the solvent molecule around the molecule, a protein, this will lead to add a lot of solvent molecule around this. And on top of this, so not only there is this long-range interaction due to the charge of the molecule, but you have also to scan a large number of configuration because the water are all independent one of the other, and depending on the position of each molecule with respect to the other, you are interested in average. So if you want to do the numerical simulation, you have to do millions of simulations of different configuration properties, so this is impossible. So due to this, chemists have invented the continuous solvation model where they represent the environment at a continuous level. So not at the point was taking into account every water molecule or solvent molecule. Okay, so they are based on electrostatic problem where the density of charge accommodate properly the shaped cavity. So this is a molecule, and this is, for instance, the solvent molecule around it. This is water, for instance. So you take well into account the specific interaction, but this is too expensive, even impossible to do. So the continuous model draw a cavity around the protein you are interested in, and then you treat this as a continuous model, and this arrives to a cheap and accurate approximation. So it doesn't allow to do everything, of course, it is a model, but chemists are working on improving the continuous model if required. The strength of this different continuous model is to be able to be combined with different types of model for the protein itself, which is either molecular mechanics, quantum mechanics, or hybrid quantum mechanics, molecular mechanics model, where you find almost every big computation now where the QM approach is taken into account to treat very specific aspects, that are at the quantum level, and the more average one taken into account at the molecular mechanical level. So what arises is that in the electronic behavior, you add, in some sense, an extra term, which is the electrostatic contribution. And as I told you, this electrostatic contribution is the result of an equilibrium between the density of the protein and the environment. So a simple model, the Cosmo model, arises in taking into account this effect where you have to solve a Laplace equation into a domain with a boundary condition. So all this to arrive just to this problem, it's a long story for something very simple. So this problem actually is not so easy as it seems, because this is a very simple, important molecule for math, the caffeine molecule, and this is typically what the shape of the molecule we are interested in, where you see roughly the molecule underneath, and you have to imagine that around each atom you have a sphere, okay? And so all these spheres do overlap, and you want to solve this Laplace equation on this domain. So the difficulty does not come from the Laplace equation, but it comes from the geometry. And it was one bottleneck of the approach. Remember that you have to solve this equation, but you have to solve it with a phi here, which is itself a result of the Schrödinger equation, or in the Hartree-Fock or Concham form that I will speak about later. So phi here is something that results from an important computation, and that is either because it's a time-dependent problem or because you are interested in the minimization of the ground state. Phi is something that will take many values along the simulation. So you have to solve this many times. If it's too expensive, then you will not be able to do your simulation. So in order to solve this Laplace equation on this geometry, what you do is to go to a representation on the boundary, which is so an integral representation. So you know that the Laplace equation is solution to the single layer problem. And so two popular discretization, either the P0 boundary element, because you are working in h-1/2, so you don't need any continuity. So this allows you to have a very nice feature for which you can use fast multiple method, but nevertheless it's very expensive. And the approach of Yor and Karplus here, where you use a spherical Gaussian centered on some Lebedev points around on each sphere. So what we proposed in alternative is to use a domain decomposition approach. This was new in the chemical framework, and actually it's a little bit new the way we treat even in the mathematical or engineer side, because what we do is to transform this problem on the integral. So we decompose this integral domain, this problem set on the boundary of this union of spheres, and we decompose it into a subdomain. So what is a subdomain? When you are working on the boundary, it is the red part, the blue part, and the green part. So this doesn't help much, but if you go to the volumic representation of this integral equation, which is that the omega is a union of sphere, now you can go to the volumic representation, solve the same problem, an harmonic problem with a Dirichlet condition that will be updated à la Schwarz, and then you solve over each sphere now, and over each boundary of the sphere when you go back to integral representation. You work on the complete sphere here. It was not on the sphere. What people would have used if they look at the literature on integral problems solved by domain decomposition technique, they would have worked on gamma equal to union of gamma high. Here what will work is gamma is a union of the whole boundary of the sphere, including something that is inside the domain omega. And this changes everything, because now you are working on the boundary of the sphere. You can use spherical harmonic, and you can go very fast. You have almost a diagonal problem to solve. And this really makes the difference, because it allows to go from 4 hours to 9 seconds. Voilà. The point is that, so this is the work done with Eric Ances and Benjamin Stam, where we looked at the influence of the number of spherical harmonics, so the degree of the approximation, or the number of spheres that are used in order to represent the molecule. So you have as many spheres as atoms, and we have a very good scaling. So as everyone knows when he is working in the domain decomposition technique, if you increase the number of degrees of freedom, you do not increase the number of iterations. This allows to have a very good scaling, parallel implementation, and this allows to go, this was the published paper, and this is now what we get. So we get 1 to 3 seconds with respect to 6 minutes or even hours when you compare this new method based on domain decomposition with the classical approaches, the fastest one using a fast multiple method. So if you compare this and this, because of the use of the fast multiple method, being not very robust, you have to choose properly the way you do the fast multiple in order to get the results, otherwise you will not get any solution. Here it is a very reliable method that you can consistently improve if you want to increase the accuracy. When you couple this with the resolution of the complete domain on the molecule, because this part here was only the resolution of the Laplace problem, okay? So when you consider now the coupling of this polarization effect with either QM method, QM method or semi-empirical method where the things are treated almost in at the mechanical continuous level. So you go from 5 units, I don't remember, it may be minutes, seconds, seconds. It's from 5 seconds to 0.2 seconds for the semi-empirical approach. For the QMMM, you go from 133 seconds to 10 seconds. And here, because the quantum mechanical resolution is more expensive, now you have to go more to the representation, and you have equilibrium. So we need to improve now the QM part because the scaling is not so favorable to the domain decomposition, but nevertheless, it is a little bit faster. But since most of the approaches are in this range, you see that there is a lot of improvement when you combine everything on the global representation of the molecule, which is the solution of the density of the molecule together with the polarization effect. So at the same time this bottleneck is solved, what we have also worked on during the last minute is to understand a little bit more the electronic structure calculation, because from this you see that the bottleneck is not anymore in the density, in the polarization effect, but on the computation of the electronic structure calculation. So working on the numerical analysis is first to work on a priori analysis, and so since there are so few papers related to this, it was almost empty route. There are some papers on the mathematical aspects of the models in quantum chemistry, but very few on the numerical analysis. Okay, so this is what we investigated together with Eric Cancès and Claude Lebris, for instance, and some of our students, to try to understand really the numerical method for used in this context. Okay, so what, for instance, for electronic structure calculation, one good example is a Concham approach, where you have to minimize an energy that takes into account the kinetic energy plus some Coulomb potential, some external potential that is acting on the molecule. So this is the integral of the gradient of rho to the square in some sense. And you have here, due to the Concham representation, a model that takes into account the correlation, exchange correlation energy, which is a function of rho provided by the Hohenberg and Kohn theorem, but which is not explicitly known. This is the difficulty. So nevertheless, we were able to do a priori analysis proving that the error in the energy in the density, in the eigenvalues of this nonlinear eigenvalue problem are optimal. So I have no time to explain everything here, but we were able to prove that a priori it works. It is useless, of course, you understand, for chemists. They don't care at all about if their method is converging, because they know it is converging. What is more interesting for them, and the a priori analysis was the first step, is the a posteriori analysis. Because the only way they can measure if they are close or not to the solution they are looking at is comparing with a real experiment, which is important. But, of course, in some cases, when they are looking for strange objects that don't exist completely, or they want to understand a little bit more about the fundamental aspects of what is happening, a posteriori analysis is important. That tells you at what percentage of the accuracy you are. So we started on this subject at the beginning of the century already with Gabriel Turinich to work on the a posteriori estimate for Hartree-Fock equation, just to prove that the Gaussian approach that chemists were using was good. So to provide them a measurement in order to know if they are close or not to the solution. Then Zhu team in China were proposed to extend this analysis of the discretization error in order to take the conclusion of the a posteriori analysis, which leads to a mesh adaptation. This is for a finite element approximation of the problem. Now, if you want to go further, you have to take into account that the problem you are solving is an eigenvalue problem. So already for an eigenvalue problem, you have to iterate generally. But due to the fact that it is a non-linear eigenvalue problem, you have also to deal with the non-linear iterations. Okay? So there you have to also consider the algorithm then. And as a toy problem with Geneviève Dusson, we start to look at this simple eigenvalue problem, which is representative of the difficulty for the Concha or Hartree-Fock problem that we have heard already about, which is the Gross-Pitayevsky nonlinear eigenvalue problem, where subjected to the normalization u equal to 1, you want to solve the ground state or the excited state for this problem. Okay. So the problem being nonlinear, you have two sources of error, the discretization parameter, and here we are in a Fourier case, so we use an expansion in cosine and sine in exponential I theta, and you have also the number of iterations. So in order to solve this nonlinear eigenvalue problem that was minus Laplacian of u plus vu plus u to the cube equal to lambda u, what we use is the linearization of this problem, which is somehow like an iteration problem, which is to solve the linear u to this equation where the nonlinearity has been fixed to a uk minus 1n, and the eigenvalue is also fixed. Okay. So this is an inverse power method in some sense, linearized around uk minus 1. So you then define also, of course, the next eigenvalue with a Rayleigh quotient. And so you have two errors, and we were able to make the a posteriori analysis in order to determine in the total error two contributions. One contribution due to the restricted expansion as a sum of exponential between k equal to minus n to n, and the iteration due to this inverse power method. Okay? So in order to understand if our error estimate here, which is an error in k iteration and error in n due to discretization, we started to put a discretization which is almost infinite, and we looked at the behavior of the error when the number of iteration is fixed to 1, 3, and increased little by little. So you see here that the error is 10 in n is 10 minus 10, so 0, because n is equal to infinity. Okay? And the error in k reveals the fact that you don't have enough iteration, because it starts at 10 minus 2, going to 10 minus 6, and 10 minus 13. The total error is the sum of the two, so it's essentially the error in K. And we have looked also on this test problem where we have the ability to know what is the exact or almost exact solution. We see that this is the exact actual error, and this is the a posteriori estimate. And you see that the ratio between the two is almost perfect, around 1. Now, if we do the contrary, which means that we put an infinite number of iterations, and we look now at the discretization error, we see that the iteration error is 10 minus 13, so 0, and the error reveals the fact that n is not enough in this case and increasing. Again, the ratio is around 1 between the exact error and the sum of the two, the a posteriori error, which is computable. For this problem, of course, where the two are computable, but for a real problem, it is only the total error that is possible because we don't know the exact solution. Okay? Now, the idea is to go, when you do an algorithm for a new problem, you equilibrate the two sources of error. So this is the red total error. The green is the contribution of the error in the discretization parameter n, and the blue error is representative of the number of iterations. At the beginning of the process, this iteration error is the largest, so you need to increase the iteration, and you don't change the value of the n, but you increase k, you iterate more, and at some point, the iteration is good, so you don't need to increase it anymore, but what you have to do in order to equilibrate is now to touch the discretization n and increase the number of Fourier coefficients that you are using, okay? So this allows you to decrease the error, the total error at a value you are willing by doing exactly the proper job, not using an expansion which is too large and not making too many iterations because this would be useless. Now we are generalizing this approach to the Concham problem with Eric, Benjamin Stam, Martin Voralik, and Geneviève Dusson. So how much time do I have? It's almost finished? 5 minutes, okay, good. So we can go now to a further instrument because we want to analyze the model. So I will go quite quickly on this. So the idea is that what you are interested in is the Schrödinger equation, okay? But Schrödinger equation, you cannot solve it. So what you do is to make some model, and this gives rise to Concham or Hartree-Fock model. I have no time to explain you. Hartree-Fock is very simple. The solution to Schrödinger problem in this case for fermion is an antisymmetric problem. So you minimize an energy over antisymmetric solution. So what you do to get Hartree-Fock is to specialize the antisymmetric solution, which are a determinant of atomic orbitals. So Hartree-Fock is very easy to understand. Concham is more complex because there is an exchange correlation functional term that I don't understand. Okay. So how can you improve this? Because Concham, you have to work on the model, and you need to be a chemist to do so. And or Hartree-Fock, but Hartree-Fock you are blocked because you use one only determinant. So what you take into account is to take better correlation model, but again, you need to be a chemist to do this. And Hartree-Fock, you can add more determinants, so you have post-Hartree-Fock method. So if you want to go to post-Hartree-Fock method, what you do, instead of using only one determinant of atomic orbital, what you do is to, once you know the atomic orbital by solving the Hartree-Fock problem, is where you take the determinant of generally the first orbitals that are the eigenfunction of your Hartree-Fock problem. What you can do is, instead of using the 1, the second, and the capital N eigenfunction, what you can do is to replace the one that is at the J position by an excited state, which is an eigenfunction that is at a higher energy. And that gives you another determinant, okay? So you have, this is a single excitation, and you can get also a double excitation or a more excitation, where you will replace a low energy molecular orbital with a higher energy one, okay, or more energy one. So this is a way to represent this, and in order to understand well this, you have to go to second quantization, which is a little bit of algebra in some sense. So if you want to take them all into account, all being in some vague sense, then you go to couple cluster, which is which is a lot of determinant, okay? And now you want to try to determine what are the proper determinants to be used. Okay, so I have no time to go into this, voilà. But what you can do is to propose an a posteriori representation of this definition of what are the excited states that are the more representative. So we have developed, thanks to previous work of Reinhold Schneider, an approach where you estimate, you mark, and you refine, like in any refinement process, where to put the importance and which determinant, excited determinant, you should have because they are more representative of the Schrödinger equation. So if you want to go to the Schrödinger equation, you need to have the proper model, and the proper model will be determined thanks to this. You have to iterate sufficiently, and I showed you how to iterate, and you have also to go to the proper discretization, and I showed you also how to take this into account. So this is the next challenge in order to go to the Schrödinger equation, to be able to take into account what are the determinants that should be used in order to go to the Schrödinger equation. Voilà. This allows us also to propose new approaches, like we did with Eric Anses and Rachida Shakir and Lian Roy, the two-grid method, where you solve on a course, at the course level, the approximation in order to take into account the nonlinear effects, and then to use this to linearize the problem and get more out of the course computation that you did. Or in addition with Tony Patera and some of his students, we have introduced also a reduced basis approximation. This was certain because reduced basis approximation is one of my other subject of interest. There is still a lot to be done, so Carlos, please join the club. And there are so many other directions, like molecular dynamics takes the time into account, and so we have been working with some of the people here on the parallelization in time in order to be able to go faster for the dynamic of the molecular, and also for quantic control with Julien Salomon and Gabriel Torinich. So all this has been done in collaboration with a group of people that I have cited. Eric Anses in first, because without him we wouldn't do any chemistry. And some chemists, thanks to Eric, we were able to join in the group some chemists like Jean-Philippe Kemal at the University Pierre et Marie Curie, and Benedetta Menucci, who is in Pisa. This was supported by this fund, and a special message from the members of the Laboratoire Jacques Williams, le laboratoire d'analyse numérique that you know well. Happy birthday, Carlo. And please come more often to Paris, we are missing you. And life is more fun and vibrant when you are around. Bon anniversaire.
We mathematicians have a strange way to show our appreciation to distinguished members of our community. What do? We force those poor guys to live for a few days with a huge group of mathematicians and to listen to thousands of talks. Thank you, Carlos. And of course the best, which as we all know are capable of the worst and of the best, improved a lot. The best only 2 days for the poor guy. The worst is this avalanche of small talks. Happy birthday, Carlos. Yeah, it's a pleasure to be here in the center of the world, as I learned yesterday. I'm still trying to recover from this statement. This event might have taken place, could have taken place, should have taken place in Paris, but certainly lots of thanks for the local organizers and all those who did it for us in some sense. Carlos knows much better the history of Chile than I do. He mentioned the Republic of Chile, the nickname of the Basque Republic of Chile. In fact, a writer, I forgot his name, once said that the Basque, always the worst and the best, imported 2 things to Chile. One was indeed the Republic, and the other, that's a word for me, the Society of Jesus. Yeah. And the worst and the best, you can go on with these, with various leaders, including dictators, which are all of Basque origin in Chile. Yeah, there is something about dictators and Basques, but anyway, private joke, sorry for that. I did change my title because I wanted to show, to talk about some subject which has some connections with Carlos' interest. And I appreciate a lot the scientific attitude that Carlos has, which ranges from theoretical analysis to numerical analysis and scientific computations and real engineering problems. So good luck with your new venture about the portable scanner. That's real engineering. And that's also what mathematicians can do or should do. So I decided to change my title. It's a strange title. So I was warned that you cannot use a blackboard, and those who know me know that okay, visualization, I suppose. Okay, so that's my replacements for a blackboard. Strange titles: defects, interfaces, and correctors. So there's going to be a little bit of blah blah. Time is running short. I'm already late. So then I'm going to talk about elliptic problems and what we call defects. It's a joint project with Xavier Blanc and Claude Lebris. Together with the last topic, which is about interfaces and elliptic PDEs, another joint project with Xavier Blanc and Claude Lebris. All this involves a bunch of publications, defects, and in the middle, defects and various other equations. If you want more details, this can be found in the videotapes that you can download from my course at Collège de France last year. Yeah, you can download them. You're not forced to do, but if you have trouble sleeping at night, I really recommend it. Just 5 minutes every evening, promise. You don't need any kind of medication. Okay. Now I want it only a single page. Okay. So even it's a little small, don't worry. So what we're trying to achieve is a systematic study of models, models meaning PDEs for us, which involve localized defects, things which are different from the background, or interfaces, with a typical scale for the defect, which is order epsilon, which might not be that small. Could be 0.1. Just to give you an order of magnitude. In a background which has a different scale, with a typical scale of order delta. The cases of interest are when the two scales are about the same order of magnitude, or when epsilon is small and delta is basically the background is constant. But you can always think that delta being small, delta being 1 is a particular case. It's just a constant situation with instead of rapidly oscillating. Of course, if you have no defects, if you have no special features in this background, then this is typically what is the goal of homogenization, to try to summarize what's going on through at this small scale. Which is with an expansion, that's a classical in homogenization theory, which is based upon the so-called corrector problem, or problem in a periodic cell. Very often it's often called problem in a cell, but it doesn't make any sense if it's not periodic. If it's almost periodic, random, then clearly you have no cell. Question 1, is the homogenization limit still valid in the presence of defects of that size? And this will depend on models, on equations. Question 2, when it is the same, can one make a more precise expansion, including in particular with the defects, so a more refined, if you want, corrector? In some sense, we consider the problem that true multiscale numerical method should solve, in some sense. Results are valid for most, essentially all classical PDEs, including time-dependent problem, but for one important case, which is tremendously more difficult, which involves wave propagation, where the typical wavelength is also of order epsilon. And then we know that all kinds of strange phenomena can happen. For interfaces, what I want to do is really to try to obtain some more precise behavior of the solution, in particular near the interface. And the typical picture you should have in mind is a periodic lattice and a big defect in the middle, or an interface, could be flat or curved, whatever, and two types of periodic backgrounds on both sides. And again, we want to focus near the defect or near the interface. Okay, so let's start. I skipped, no. So I think there is basically there is something missing. Sorry about that. I shouldn't do that. So clearly, when it was scanned, a page disappeared. So it's going to be, in this way, it's going to be faster. Basically, what you do is you scale out. I want a blackboard. So what you do is you take an elliptic equation, fast oscillating coefficients, and the coefficients are the sum of periodic coefficients called Aij periodic. They don't appear. So inside Aij, you have two contributions, the periodic contributions and some local defects, which means that coefficients change, and change in a way that goes to 0 as x goes to infinity. If you make the usual ansatz, the homogenization ansatz, which is just scaling out the small scale, if you just scale out the small scale and subtract the non-periodic corrector, what you're left with is this elliptic equation in a whole space. It's no more in a periodic cell, which involves the sum of those coefficients. And on the right-hand side, you have all the rest, the various contributions that involve the periodic, typically the divergence of the periodic the gradient of the periodic corrector times the perturbed coefficients. So this is all the garbage which comes from subtracting the periodic background, and clearly you also have some decay on the F guy, which is in the right-hand side, and the decays are similar for those additional coefficients and for the right-hand side. That's what you obtain by just plugging in the usual ansatz for homogenization and subtracting the periodic corrector. So you're left with an elliptic equation in the whole space, and you may say, we know everything about it. No. We know very little about it because there are no zero-order terms, there is no nice coercivity because the decay may not be fast enough for lots of reasons. And even if you have very fast decay, the behavior of the Green's function, which is precisely what is going to give you solutions, can be awful in principle. because the behavior at infinity of Green's function is very much related to the properties of coefficients. So although it looks like a classical problem, it fits not in the literature, but in the cracks of the literature. So there are several results that I'm going to summarize in 3 minutes to have time to discuss the other topics. So that's the simplest elliptic homogenization and in presence of defects. And the only easy case in dimension greater than 3, or in dimension 1 you can solve explicitly, is the one that I quoted as theorem 0. But first, I have to explain something about U being sublinear. Indeed, when you solve Laplacian U equals 0, certainly you have the Laplace equation. The corrector means, if you have the Laplace equation, means that you have no defects, perfectly homogeneous. So the corrector should be 0. Okay? So the right solution is 0. Everything is defined up to a constant. That's something I don't want to get into. But certainly you have linear functions. And linear functions should be discarded because typically the solution of the homogenization problem, which represents most of the action, the periodic background, when you scale it out, it becomes a linear function. It becomes Px. So you want to be able to distinguish between the what corresponds to the background and the correction. So that's why at infinity the corrector should be sublinear. Okay? And we will see that in some cases those correctors exist and do not go to 0. So that's why it's not a classical problem in elliptic equation. So sublinearity. We are well used for homogenization theory that as soon as you deal with even quasi-periodic homogenization or random homogenization, the correctors are not bounded in general. That's a very strong property, but they have to be sublinear because otherwise they wouldn't be correctors. Okay, so sublinearity is absolutely crucial. So the first case is when you have an L2 setting, if f and b, so everything, all the coefficients are going to be smooth. So I'm going to measure the decay at infinity in terms of LP. So the higher p is, the less decay I have. It's not a question of regularity. They are all bounded. Okay, so if f and b are in L2, then there exists a unique solution, which is in, the gradient is in L2, u is in C0, u belongs to the Hilbert space. This is Lax-Milgram in the right space, which is the usual variation of H1 in Rn when you don't have the L2 norm. So that's completely classical. You just here use the coercivity of the coefficients, the coercivity of the definite positiveness of the matrix, and you're done. So that's trivial. And that's the only case which is trivial. Now let's move a little bit further. What kind of decay is borderline? So first of all, it depends whether you want a corrector that decays at infinity or not. So if you take now f and b in LP, and then p is between 2 and d, in d you have to replace LD by LD1, Lorentz space, forget it. Then you can show there is still a unique solution u, which is continuous and goes to 0 at infinity, and various other properties that I don't list. And this comes from a new estimate which has nothing to do with anything. It's absolutely general. Whenever you have uniformly elliptic operators, you can bound the Green's functions independently of anything in the following way. You bound it in some Markovitch space, which are exactly those you would expect from the decay of the Coulomb potential or the fundamental solution of the Laplace equation in RD. You know that the fundamental solution is 1 over RD d minus 2, and that's how you obtain almost LD over d minus 2 integrability, almost d over d minus 1 integrability. This is a rather simple lemma to prove if you have the right tools. So you can do this either by symmetrization techniques or by renormalization techniques. Fine. So once you have this estimate, it's not difficult to prove theorem 1. The real hard one, and here I'm going to slow, is that in fact any LP would do. It's plausible that when lift these to L infinity, but then one has to deal with BMO spaces and so on, so that's a little bit messy. and I was not brave enough to try to push that. So any kind of decay will do, algebraic decay will do, since theorem 2 is valid, and it's true in all dimensions. If f and b's are in LP, for p greater or equal to d, there exists a unique solution up to an additive constant such that du is in LP, which is a maximal regularity. Look, on the right-hand side, f is in LP, and you say that du behaves like f. Okay, so that's maximal regularity. So du is indeed in LP, and you have this growth, which with an exponent alpha, which is 1 minus d over p. That's the Sobolev, that's a Sobolev exponent, which translates into the growth you can expect from the solution. In general, in those cases, including in one dimension, the solutions are not bounded. Okay, so you can't expect to do any kind of classical elliptic theory to get solutions like that. That's out of the scope. This comes from the fact that you have an estimate, which is this inequality. This inequality for, in the case of coefficients, which are given by periodic coefficients plus something that decays at infinity. This is the maximal regularity estimate, depending only on the coefficients. du in LP is formally bounded by constant times f in LP. At that point, I want to remind you a few things about elliptic regularity. We are used to this type of results when we look at an elliptic equation, let's say in a bounded region. That's coefficients are smooth, that's classical theory. It's okay also in RD. When you look at the minus Laplacian. What is du? It's the gradient of minus Laplacian minus 1 of divergence. It's a product of two Riesz transforms, and we know that the Riesz transforms are bounded in LP. If you take general coefficients, even if they are smooth, uniformly smooth, this estimate is wrong. Because there is no scale. You can rescale this estimate, right? There is absolutely no scale in this problem. So this means that this estimate means that if you rescale, you replace aij by aij of x over lambda, where lambda is a new scale. And this estimate is independent of lambda. So this estimate shows maximal regularity, in particular if you were to consider the homogenization problem, letting epsilon go to 0. And that's an hard estimate. Okay. In fact, in the periodic case, yes, here it came. Okay. Moved. Okay. In fact, in the periodic case, this is known, and that's due to Avellaneda and Lin. It's a very interesting result based also on the use of correctors. So why is it true? It's not the proof. Why is it true? Well, at infinity, coefficients are small. It's a perturbation of periodic. So the estimate should be true if we were able to localize for x large. In a finite volume, it's true because the coefficients are smooth. So it's plausible, it's true everywhere, except that you can't localize because there are no scales. So when you have a scaleless problem, the localization is a delicate matter. So you can't localize. I mean, you can do something like localization, but it's a very odd proof. And it's rather funny to see that, anyway, it's fun to see that this problem led, although we thought we knew everything about elliptic equation, that it led to a question that we had no clue on for elliptic problems. Briefly, I want to mention that the situation gets even worse when we enter nonlinear equations for which we know homogenization. Because for those problems, if we don't know homogenization, we can't even begin. Okay? So in particular, if we were to consider things like conservation laws, we know very little about the homogenization. There are only partial results about that. Very limited results. So aconal equation. So in some sense, if you think about geometrical optics, it's a very high frequency, except that the way Hamilton-Jacobi equations encode what's happening after the caustics is a problem. But roughly, it gives a first a little glimpse on what's happening at wave propagation at a very high frequency. And then we will see that lots of things happen which are a bit more complicated. So the typical example would be the homogenization or the perturbed homogenization of this aconal equation. Typically, the same will happen with a d phi over dt instead of phi. It's simpler to write. You have a periodic index, that's essentially the index, and you add some perturbation of the index, which means that the medium is being perturbed, and that's the f. Just, you could have a more complicated function, just to give an example, and you can do general Hamilton-Jacobi equation and so on. Lifting everything up to a constant, you can always assume and normalize the periodic index to have 0 minimum, okay? So it's just a matter of normalization. So the first question is whether we get the same behavior as the original homogenized problem, and the answer is no. Unless f is, and it's an if and only if, unless the perturbation has a sign. So as soon as you have a tiny negative perturbation, the homogenization is just false, goes wrong. You have trapping at those points. Let me remind you what happens with the homogenization. That's one of my favorite papers, a joint paper with Papanicolaou and Varadan, which was never published. So the preprint circulated, was quoted in a decent number of times, but was absolutely never published because we wanted to do another case, namely the random case, and we got stuck. So we left it like that. But I'm very proud that one of my most quoted papers has never been published. Just fooling around with the indices, you know, the H like hemorrhoid index. That's fun. But anyway, for all P in RD, that's what we know is that there exists a unique constant, which is the homogenized Hamiltonian, such that there exists a corrector, not necessarily unique, periodic, which solves the Sal problem. And just to give an idea is that in one dimension, the effective, the homogeneous Hamiltonian is this thing. It's affine, like the original one, which is the absolute value, but it has a flat part, okay? It has a flat part which stops at the average of the periodic index, right? So this is a very interesting behavior because this means that in the flat part there is absolutely no propagation. Propagation disappears because of the oscillations. That's very much related with this very naive, very simple, Hamilton-Jacobi formulation. It's very to the so-called invisibility cloaks, okay? This is really about trapping lights. But anyway, so here's the theorem, is that if you have two cases, if the homogeneous Hamiltonian in general is 0, and if f has compact support, there exists a solution. And if f is non-negative, because otherwise already the homogenization is wrong, then there exists a corrector which coincides for x large. There is no perturbations for x large. With u equal v periodic, the corrector is the same as the periodic corrector for x large. What that means is that if f is compact support very far out, you have exactly the same behavior because in some sense the light rays are being trapped. They are being trapped in the periodic case, that's the flat zone, and so they don't see the local perturbation. Okay. If h bar is strictly positive, and if f decays fast, slightly faster than 1 over x, then there is a solution, and the difference with the periodic corrector is bounded. The final remark is that if d is equal 1 and you're in the trapping region, if f is strictly positive everywhere, even if it decays as fast as you want, there are no solutions. Again, it's a very fine behavior that forces us to understand much better the equations we thought we understood. Quasi-linear equation, so same type of equation. The first question, the answer is no if f is too negative, and yes if f is positive. The yes and no depends on the properties of the certain Schrödinger potential, Schrödinger equations. I don't want to give too many details. But the bottom line is that if f has the right sign or not too negative, then indeed there exists a corrector, and that's okay. This is again not so easy, but the fun part is to understand the connections with Schrödinger operator, and that's something I really don't have time to explain. Fully non-elliptic equations, that's again the situation where, depending on the uniform ellipticity properties, you have correctors that have different behaviors at infinity. Once more, linear or nonlinear, the things that are playing a role are things which are Green's functions or like Green's function. And as soon as you're not in you're in a whole space and you don't have lots of information about the coefficients, the behavior at infinity, the understanding of those Green's function is not something which is so easy. Let alone that you don't know that they exist, and for nonlinear problem, what does that mean, the Green's function? Let me conclude with interfaces and elliptic equation. In terms of homogenization, this is completely clear. Let me take a flat interface. In terms of homogenization, we know what's happening. Homogenization theory, it's a variant of homogenization theory. You have the homogenized elliptic problem on one side, the homogenized elliptic problem on the other side, transmission along the interface, right? But as S epsilon goes to 0, can you say more? And the answer is yes. There exists a corrector which is sublinear, which is bounded in some cases, and you will understand what it means in terms of irrational properties of the various periods. So in order to make the problem a little bit simpler, what I'm going to describe is a quasi-periodic problem, because in some sense, here you're, through the Steklov-Poincaré problem operator, you can reduce on the problem of the interface, and you're going to have the sum of the contributions. So in some sense, you're taking a trace on an hyperplane of a periodic stuff. What you create in that way, depending on the various angles that appear, is something which is not necessarily periodic. It depends on rational properties. So it is typically quasi-periodic. And then you may have another quasi-periodic inference coming from the other side. So let me take, for instance, a two-period situation. X is now in RD. Let's move, instead of having operators which are a little bit like square root of those operators, let me describe an elliptic operator. So uniformly elliptic situation. Now I have a quasi-periodic problem with two periods, x and y, okay? And different periods in x. X has several coordinates, y has the same number of coordinates, and they have different periods. If Tx and Ty, which means component by component, are rationally dependent, it's a periodic homogenization problem. Take just a bigger period, okay? If Tx and Ty for some directions are rationally independent, well, that's a true non-periodic, quasi-periodic problem. Existence of a corrector, okay? There are stuff in the literature that tell you quasi-periodic is a particular case of almost periodic. There is a literature on almost periodic homogenization. I pretend it's misleading, okay? Why? Because usually they play by saying almost periodic is a particular case of stationary through the compactification, the Born compactification of RD. But what they forget to say is that once you play with the Born compactification of RD, you create an R measure, which is the measure which is independent by translations. And you can show very easily that the measure of the initial physical space, which is RD, inside that compactified set is 0. Okay? Very simple. You restrict the measure to RD, it's translation invariant. So it has to be proportional to Lebesgue measure. It has finite mice, it has to be 0. Okay? So this means that any result which says there is an almost everywhere corrector is completely useless. Okay? And the same will appear here, because when you, even with quasi-periodic and two periods, if Tx and Ty are rationally dependent, so this is pure homogenization in some sense. Huh? If Tx and Ty are irrationally independent, here's the problem, the typical corrector problem that we would like to solve, except that now we have two irrational periods, or sets of periods. And we, again, request the solution to be sublinear. So the theorem is that there exists a unique solution such that gradient u is the trace of a quasi-periodic, of a periodic function in xy, and u is smooth, u is in general bounded. And if the ratio of period is not a Liouville number, then u is as good as in the periodic case. So it's u itself is quasi-periodic, and it's bounded. What is a Liouville number? A Liouville number is something which can be very well approximated by rational numbers. So non-Liouville is quantified in this way, that whenever you look at lambda minus p over q, it's greater in absolute value than a certain constant q to the power s, and s has to be greater or equal to 2. That's classical number theory. This is exactly the type of proof is that you look now in the doubled variable problem. You replace, you have two variables with the same x. Now you go to x and y. Okay? So now you have a true periodic problem, okay, in xy. Of course, you're interested at what's happening in x equal y. So you have to solve a degenerate equation, because otherwise you would compromise what's taking place at x equal y by all the rest. So typically what you should do is take an elliptic operator only in the direction x plus y. Okay. So they play the same role, and you don't diffuse you diffuse, the diffusion is taking place just along diagonal. So that's why you can restrict the solution and the equation on the diagonal. Let me write d for dx plus y. It's not too difficult. That's the analog of elliptic regularity to get estimates on du in all Sobolev spaces if the coefficients are smooth. And that's good enough for the first part of the theorem, because not only you want to build a corrector, but you want to be able to restrict this corrector to the diagonal, y equal x. And that's exactly what I was saying about the almost periodic situation. We are in, let's say, take the one-dimensional case, lifting to doubling the, when you double the variables, you have now a square in R2, and you're interested in a diagonal. The diagonal has zero measure in the square. So if you solve this and don't get extra properties that allow to restrict on the diagonal, you have done nothing. And so this, in general, you can do it on u. But du starts to be regular in all directions. So you can do the restriction. And if it's non-Liouville, you can think of this in terms of Fourier series. You have some kind of Poincaré inequality with loss. Here you should subtract a constant, so phi has zero average. Except that this is a weird Poincaré inequality where you lose derivatives on the other side. So, and s minus 1, s is the power which comes here in the lack of approximation by rational numbers. And so once you have that, you have estimates on du, then you get estimates on u, and you can build the correctors. It's slightly weird, and you may ask, well, you know, in practice, especially if you have a curved boundary, I'm going to change from one situation to the other. Yes, from one point to the other on the boundary, the corrector is not going to have the same properties. But what you can show is that they are uniformly sublinear, independently of all the possible rational properties. So that's fine in terms of an expansion, in terms of understanding what's happening. In fact, all this is very much related to when you are solving equations of that type, correctors equation. This is very much related to ergodicity theory for diffusion processes and the large time behavior of parabolic equations. In fact, not only in order to be able to solve what probably is called the Poisson problem in ergodic theory, not only do you need to have ergodicity, but you need to have ergodicity at a rate which is good enough so that you will be able to solve those corrected problems. So that's why after last year course on such issues, this year my course is on indeed ergodic properties. Again, if you really have tremendous problem with sleep, I recommend downloading those further videotapes. So there is an infinite reservoir of stuff. If you want, you can have a different videotape for each evening, you know. So, so you should be safe. But let me explain, I'll conclude with that. Let me explain let me explain why the rational properties of lambda plays a role in terms of ergodicity. Ergodicity means what? It means that we have something like Brownell motion oscillating very quickly, and which is now moving, let's say, in 2 dimensions, but it's moving on the diagonal. Okay? Now, if the ratio of the boundaries of the it's not a square, it's a diagonal, but it's a rectangle, and the sides are precisely the periods. If they are rationally dependent, okay, you're going to stay on essentially the same line. It appears, but it will repeat itself after a while because of a rational dependence. Okay, no ergodicity. But you can still solve for the problem because in some sense you solve it in 1D. You just look at what's happening on the side. As soon as it is irrational, you started filling the whole rectangle because of periodic properties. So there is no possibility of reduction to 1 dimension. And how fast it's going to be fill the square? If you are close to rational, it's going to fill the square, the rectangle, slowly. If you are far from rationals, it's going to fill the square more quickly. That's how the Liouville properties have been used over and over in various fields of mathematics, including dynamical systems, camp theory, and so on. But the connection is always the same. This is a way to measure how quickly you fill a line is going to fill the rectangle, right? So about Liouville numbers, I don't care about Liouville numbers. It was just fun to see this appearing in a very natural fashion in classical homogenization theory. Just for our information, the Liouville numbers are not only dense, everything is dense, but except those things which are not dense. Well, sure. The set of Liouville numbers has full measure, okay? But the complement is a bare set, so it's not that small neither. Okay. There are many further interesting questions on such questions which are related to quasi-periodicity, almost periodicity, but I wanted to emphasize that we know so little about the almost periodic homogenization, which is, should be a problem that we understand everything about nowadays. That's not the case. And beware of what's written in the literature, okay? So with this, one more word is that I said I indicated my appreciation, or even my admiration for the scientific perspective that Carlos has, but what I admire even more are the human qualities and the kindness towards others. That's much more important than mathematics, and you mentioned that in your presentation, and that's what's really important. So thank you very much, Carlos, and yeah, happy birthday despite talks like that.